That's what I'm talking about. Rockets, baby. NASA is working on our next generation of rockets and spacecraft that are going to take us back to the moon and all the way to Mars. What you are watching is the 9th annual NASA Robotic Mining Competition. Thank you for joining us. If you've just poked your head in the tent because it looked interesting, you are in for a treat. You're about to see some robots competing against each other. These robots are built all year long by college and university teams from all over the country. We have 45 teams that are here on site competing this year. And the mission of these robots during this competition is to dig and excavate and collect as much of the gravel and rocks that we have buried underneath the topsoil as much as they can in 10 minutes and take those rocks and transport them back to the starting position and deposit those rocks onto a hopper that simulates the lander that the robots were dropped off on the surface of the moon or on the surface of Mars. So we're simulating a robotic mission, an unmanned robotic mission that is on the moon or Mars that is collecting not rocks. We're actually using the rocks to simulate icy soil or chunks of ice that are buried beneath the surface. And we think that we're fairly certain because of instruments that we've sent to the moon and to Mars that there is ice under the surface. And so what do we care about ice on the moon or Mars? Well, it turns out that is a precious resource on the moon or Mars. We can take that ice and we can turn it into some very useful things. We can turn that ice into water, and our astronauts can actually drink it. We can turn that water into hydrogen and oxygen rocket fuel. And so there's a lot of reasons to collect ice or water on the moon or on Mars. So this competition is actually helping advance those technologies that NASA's going to be using someday in order to help live off the land when we're living on the moon or on Mars someday. On the screen you can see a 6-minute timer. Started out at 10 minutes, there's 6 minutes remaining. The two teams that are getting ready to run their robots are Texas A&M International University, TAMU, on the A side. And on the B side, we have the University of Portland. Both of these teams getting their robots ready. They have 10 minutes to get their robots ready to compete in their first of hopefully 2 competition runs. Our schedule allows for each of the 45 teams to get 2 official runs in this week. And we're going to try and get that done even if weather comes and gets in our way. Both of these teams have been here in this competition in years past, so they have experience in this competition for many years, although we did change the rules up significantly this year. We try and change our human missions to the moon are actually going to be great practice for our human missions to Mars later on. And so even though we could probably live on the moon for quite a while without using the resources that are on the moon, it's actually great practice to live off the land on the moon too, even though it's only 3 days away, and use the resources that are on the moon and test out these technologies and work all the bugs out, so to speak, and then we'll have more confidence to take that same equipment to Mars, where we really will have to live off the land because it is a lot harder to send all those resources all the way to the moon or all the way to Mars, which is a lot further than the moon. Now, all the technologies that NASA is inventing, you may wonder, well, how can how can my university get a hold of some of these technologies or some of these resources that NASA has developed? Well, NASA has a technology transfer office. If you go to the website technology.nasa.gov, you can see all kinds of NASA technologies that NASA has worked on and has invented and that are actually available for small companies or individuals to go ahead and make use of. All right, in just a few minutes, these robots are gonna start. Joining me on stage is Al Feinberg from NASA Education Office. Is that correct?
That's right. Yeah, I'm Public Affairs Officer representing Education and several other directorates, but primarily the Education and RMC.
All right. Well, thanks for joining me. You can see we've got a great crowd here in the arena, and we have several hundred people watching us online on our live stream, which is at bit.ly/NASA RMC. That's bit.ly/NASA RMC. So hopefully everybody's sharing that address on their social media accounts so that all their friends and family back home can watch this competition along with them.
And if you're posting to social media, the hashtag is RMC 2018.
Yes, hashtag RMC 2018. Now, you can see robots moving. This competition is underway. We've got Texas A&M International University, and we've got the University of Portland. Both of these teams have been here several years. And the Portland robot on the B side is, look how high that robot is. That robot has no problem with the obstacles, not the rocks and not the craters that we've put into the, you can see their six-wheel rocker bogie suspension design is very similar to the NASA Curiosity rover.
That's right. And it looks like they operate independently of one another, too.
That's true. You can see how it turns in place. Each wheel can actually rotate its position in order to spin in place or to drive like a tank.
Wow, look at that.
It's pretty impressive.
Now, I'm not an engineer, but would we say that they're spreading out their mass?
Yeah, there's a lot of pros and cons for decision on how many wheels to put on your robot. The more wheels can spread out the pressures. You can make bigger, wider wheels. You can make larger diameter wheels. You can make fatter wheels, wider wheels, and all those decisions help distribute the mass and distribute the forces of the driving. And so there's a lot of decisions that these students have to make.
What would be the downside of that? Because I would think that you'd want to do that all the time, but why would somebody design, get away from that kind of design?
I think the downside of the six-wheel rocker bogie suspension is it's more complex. So you've got a lot more parts that have to work together and not break. And so sometimes simplicity is your friend. So there's risk. There's definitely risk in having a more complex drive system like this rocker bogie suspension.
Looks like the Aggie auger was moving a bit.
Yeah, it just moved. So the students are probably testing all of their actuators and trying to figure out why the robot hasn't moved yet. Now this Portland robot, it has a bucket ladder digging system in the middle that hopefully we'll see it lower soon. They've turned their robot sideways for the digging, and you can see it lowering right there in the video.
Now the students in the booth can't see as well as we can out here, correct?
Right. They cannot see that video feed that we were just looking at. They do get a video feed that is the lander's perspective from the reverse angle, but it is a low-quality video feed, so they don't have the high-resolution camera feeds that we have access to. There you see the students, both the TAMU students on the left and the Portland students on the right, as the Portland students control the robot, and as the TAMU students, I'm guessing, are troubleshooting right now. I noticed that the Portland robot on the right, when it dropped its digging apparatus down, it was not quite over the orange line that it needed to be over to start digging in. And so I'm guessing that's what the students have also realized, and they're moving their robot further over into the digging area.
It appears from that shot that they've done that, in fact.
Yeah, so the lower shots on your screen are actually the views that the students can see. And the upper shots are not viewable by the students. There you can see their digging mechanism lowering down. On the Portland robot, not only does this Portland robot have wide wheels, but you can see there's grippers, there's pieces sticking up from those wheels that allow the robots to grip.
Almost a reverse
crushed
tread.
rock. Mm-hmm. There's a good shot of the digging. Now you can see it kind of bind there. That's a good visual example of how this crushed volcanic rock can resist your digging forces, and the students had to figure that out. The students are actually given research papers that describe this material that they have to dig in. Because these students are not going to have this material. These students are not going to have this material back at their school. They're going to, most of them, test in sand or something that's a lot easier to dig in. And so they're given research papers that NASA scientists have created that describe all the physical and material properties of this crushed volcanic rock so that they can try and design their machine in a way that can maximize its digging.
Now, this simulant came from outside Flagstaff, Arizona, correct?
Yeah, Black Point, Arizona. And it's actually a large volcanic lava flow that is dormant. It's an old lava flow, and this is basically just crushed up volcanic rock left over from a manufacturing facility out there.
NASA has conducted a lot of analog research there and has studied using robotics on the surface there, as well as astronaut training.
That's true. The lava flow out there, it's a very big surface area of bare lava rock, and it looks and acts a lot like the moon or Mars when you're actually out there working on it. And so a lot of different NASA analog missions have gone out there in order to practice their practice with robot technologies that they've developed, practice with their astronauts and different tools that they've developed to see how they work in that environment. We only have 3 minutes left in this run, so the Portland robot did obviously do some digging. So at some point, it's going to have to decide it's time to go back and dump the onboard material that it's collected. And sadly, I haven't seen the TAMU robot on the left. I haven't seen the wheels move. We did see the auger move earlier, so that implies that they do have good communication if they're able to command their auger. So that kind of implies that there may have been something that is not a communication issue, that is something else. Hopefully we'll be able to get a chance to talk to these students from both of these teams and get a feel for what their perspective was during the run and what they think happened.
One of the things to point out is that we learn from failure, and that is something that NASA teaches and preaches, and these students are understanding themselves. This is a way to prove or disprove certain designs and functions and know how to improve upon that. So failure is an option in a sense, in that it provides a learning opportunity.
That's a good point. NASA is very famous for the saying, failure is not an option. And that came from the Apollo 13 moon mission when we had astronauts, halfway to the moon, and there was a problem, and we have got to do everything we can to get these astronauts back safely. Obviously, failure is not an option in that case, but in unmanned research, projects and missions, especially in the research and development world, like over in SwampWorks where I work, failure is totally okay as long as it's not hurting anybody. You always learn from failures, and so if we were afraid to try new things, we would never advance in our research. So in that world where you don't have human lives on the line, failure is definitely an option and is not looked down upon at all. It's actually celebrated in the right groups, that have that mentality. Okay, we're within the last minute. I don't know if Portland's going to be able to, in this short a time, going to be able to get back. I haven't seen the robot move in a while, so they may have had some sort of okay, their digger is moving. So that's interesting. They haven't lost communication with their robot.
Only 30 seconds to get back to the hopper, though.
That is not a lot of time. So it'll be interesting to talk to the students when they come out of the control center and find out what they think happened with the robot. Now, they may have no idea. It depends on what their computer screens are telling them, what kind of real-time feedback, real-time data they're getting from their robot, their motors, their sensors, their power system. These robots are, complex systems of systems. And so as time runs out on both of these teams, they will get a second chance, hopefully, later on the week. Let's give a big hand to Texas A&M International University and University of Portland. Al is going to go see if he can grab the students as they exit their control room and talk to them. So hopefully we'll be able to hear from those students and find out what their perspective is on that run. Now, don't go anywhere, and make sure you share our hashtag on social media, hashtag NASARMC, and make sure you share our live feed so that all your friends and family can watch along this competition with you and enjoy it with you, and share in the moments of success and share in the moments of agony with you in this competition. So we thank you for your interest, and thank you for posting on social media and keeping the word going about this event and keeping the excitement going. So don't go anywhere, and the next two teams are going to be coming into the arena soon. And those two teams, just to give you a heads up, are New York University and Illinois Institute of Technology. So in just a few minutes, we will start the run for those two teams. So don't go anywhere. This is the NASA Robotic Mining Competition, our 9th annual, and hopefully we'll be able to continue many years to come this competition because it is a really great competition. All the students get a lot of great experience out of it. NASA gets a lot of great looks into new technologies that we hadn't even thought of, new ways to drive on this simulated regolith, new ways to dig in it, new ways to transport it and dump it. So everybody wins in this competition. There are no losers. So in just a few minutes, stay with us, because in just a few minutes we're going to start New York University and Illinois Institute of Technology. Thank you for your interest, and don't go anywhere. This is the 9th annual NASA Robotic Mining Competition. Be back soon.
Hey, everybody, I'm with Emmett from the University of Portland Pilots, and first of all, I got to tell you, you're the best-dressed interview we've had so far. So what happened there? You guys seem to start out okay.
We're really happy with how we started out. The driving system worked excellently. Our suspension was amazing, but we were having an issue with our bucket chain. So we have two gears that get a lot of backlash, and it got stalled.
So you did dig, and you got some simulant in there. What are you going to do to correct the problem at this point? What do you think you're going to need to do?
We need to work on our tolerances in our gearbox, and so we have better gear meshing, and that will enable us to not stall when we're digging up that BP1.
As a non-engineer, how would you do that given the amount of time you have to work on this?
Mm-hmm. So we're going to have to just add some more support. Really, it's just going to be another gear, maybe some more aluminum, and that'll keep our gears from moving.
And that's something you can work on right here.
Absolutely. The bot shop will help us with that.
Well, we wish you the best of luck on the next run.
Thank you so much.
Thanks, Emmett.